from Berkeley, who's going to tell us about mathematical applications of a six-dimensional string theory.
Okay, I'm very happy to be here to have an opportunity to tell you about this work. So this is work with Andrei Okunkov and earlier work with Edward Frankel, and also work with my student, which plays an important role in the story. Okay, so Simon's work has played a pivotal role in developing the mathematics of gauge theories, both directly and also by influencing and inspiring the work of others. So this talk will, despite its title, will actually be an illustration of the importance of gauge theories for understanding many problems in both mathematics and physics, even those that at the outset may not be related to gauge theories. Okay, so our starting point will be a quantum field theory in 6 dimensions, which is not a gauge theory. So this theory is labeled by a choice of a simply laced Lie algebra G. It's a 6-dimensional theory which has conformal symmetry and something called 2-0 supersymmetry, and its existence is predicted by string theory. So this theory, which we'll call theory X for short, is remarkable in part because it's expected to play an important role in pure mathematics. And in particular, it's expected to play an important role and give us insights into geometric Langlands program and the knot categorification program, as we've learned from works of Oguri, Vafa, Kapustin, and Witten, and so forth. Now, there's a serious obstacle to making progress, which is that even by physicist standards, this theory is very hard to understand. It's hard to understand because it turns out not to have a classical limit. So one should contrast this with gauge theories, which have a classical limit, which is described by an action functional for a g-valued curvature f. And this action is the starting point is the classical description of the theory and a starting point for basically any question you want to ask about it. So for this theory X, this is not available. Now, it turns out that one can make progress by replacing this theory X, which is a point particle theory, with supersymmetry and conformal symmetry, by a 6-dimensional string theory which contains it. And that string theory is called the 2-0 little string theory, 2-0 for the amount of supersymmetry. So the little string theory is labeled by the same AD Lie algebra G, and you can view it, and it should be viewed, as a one-parameter deformation of theory X. The parameter that you vary is the characteristic size of the string. So in the limit that this vanishes, you get a point particle theory, which is the theory X. And the theory is called little string theory because it arises as a small piece of the full 10-dimensional type 2B string theory, compactified on an AD surface of type G, labeled by the Lie algebra G. Okay, so now the reason that it's useful to work with little string theory is as follows. It turns out that for many settings of interest in mathematics, this theory localizes, essentially due to supersymmetry, the theories on its defects. And in little string theory, the theories on the defects turn out to be supersymmetric gauge theories of the kind studied extensively both by mathematicians and physicists. And that's something that my student and I understood. And in fact, the gauge theories on the defects turn out to be very close cousins of the gauge theories that arose in Donaldson's work, differing only in dimensions, but the same amount of supersymmetry. And in fact, sometimes even the dimension is the same. Yes?
What do you mean by, and what do you understand by defect?
So you don't study the 6-dimensional theory in vacuum, but for interest, because that would be too boring. In fact, nothing would happen. You want to put some kind of you put some literally defects in the everyday sense, and on those defects will support gauge theories. Okay, so they're like sheaves if you want. Okay, in a geometry setting. I'm not sure which language you're familiar with, but hopefully it will become clear.
There can be Gordon's point, like in third-dimensional one, they're like boundaries. The CFT correspondence is that.
That's right. So this in here, it's codimension 2, 4, and 6 defects that end up playing a role. Okay. So codimension 4 defects in a 6-dimensional theory would be 2-dimensional, and they would be like world sheets of strings. Okay. Anyway, so with this insight, it turns out that from physics of the 6-dimensional little string theory, one can in fact get some mileage into geometric Langlands program and the knot categorification program. And that's what I'll try to explain. Okay, so Bailenson and Drinfeld formulated geometric Langlands correspondence in the early 90s, and in the original paper they explained that one can phrase the correspondence in the language of 2-dimensional conformal field theory. So one can interpret geometric Langlands correspondence as correspondence between conformal blocks on a Riemann surface C associated to a Langlands dual pair of Lie algebra, G and LG. So on the electric side, are conformal blocks of WCW model or F1 current algebra associated with LG at what's called the critical level, which is roughly speaking which is essentially infinite coupling. And on the magnetic side are conformal blocks of what's called the W algebra associated with group G in the classical limit. So proof of geometric Langlands was given in this context for bundles with open structure by Bailenson and Drinfeld, and later by Frankel, Gaisguri, and Villanen for bundles with ramifications. Now, there are two ways you might try to generalize this.
So are you going to tell us what the conformal blocks are?
They're not quite partition functions of a 2-dimensional conformal field theory, but partition function of a 2D conformal field theory will factorize into holomorphic, anti-holomorphic pieces, and this is a holomorphic piece.
I remember in connection with the Berlinde theory, saying that is that the same thing? The Berlinde's theory would be relevant for braiding. It's related to that. So
you didn't mention Witten's work.
So you can think of it as just chiral correlation functions. Okay, we'll get to Witten's work. Just bear with me. We'll come at it from a different angle, but we'll get to Witten's work. Okay, so one thing that's natural to ask about is to deform this chiral algebras away from the critical level or equivalently to finite beta. And this is the quantum Langlands correspondence. Another thing you might try to do, though it might seem bizarre at the outset, is to replace the chiral algebras with conformal symmetry by by the Q-deformed counterparts. So the Q deformations of the relevant CFTs were studied over the last 30 years by mathematicians, and in large part with motivations of geometric Langlands in mind. Whether the thing itself is a good thing to do was not obvious at all. Okay, now it turns out that one can implement both generalizations, and in fact it's easiest to do it at the same time. So in the joint work with Edward Frankel and Andrei Okunkov, we formulate, for the lack of a better word, quantum Q Langlands correspondence.
It's still the geometric line.
No. Well, yes, it's still geometric in the geometric world, that's right. But at finite coupling, and then you do this funny Q deformation. So, and this correspondence will be an explicit linear map between Q conformal blocks associated to chiral algebras corresponding to a dual Langlands dual pair of Lie algebras. Okay. So, so we'll conjecture the correspondence between Q-deformed blocks on a Riemann surface C, where on the electric side one looks at conformal blocks of what's called the quantum affine current algebra, which is a Q deformation of LG hat at level K. This quantum affine current algebra was defined by Igor Frankel and Nikolai Reshetikhin in the 80s as the first example of a Q deformation of a CFT, of a two-dimensional conformal chiral algebra. In this case, the one with affine current symmetry. On the magnetic side, we'll get Q-conformal blocks on the same Riemann surface of a Q-deformed doubly algebra associated with G. And this deformed doubly algebra, so it's a Q deformation of the ordinary doubly algebra with conformal symmetry, and was defined by Edward Frankel and Nikolai Reshetikhin in the 90s. Again, with geometric Langlands applications in mind. Okay, so the conformal blocks we'll be relating are, in fact, the very vanilla ones. On the electric side, those are the ones that were defined by Igor Frankel and Reshetikhin in the original paper. So they're correlators of chiral vertex operators sandwiched inserted at some points on the Riemann surface, sandwiched between some states. So the vertex operators transform in finite dimensional representations of the quantum affine algebra, labeled by corresponding to representations that lift from representations of LG. And again, they're inserted at points on the Riemann surface. The states you sandwich them in are just Verma modular representations of the algebra. And that's it. So the one restriction we put is that the Riemann surface we'll study the theory on is an infinite cylinder with punctures, and punctures are labeled by the coordinate and a representation of LG. Again, a finite dimensional representation. Okay, on the magnetic side, the data is the same. We have the same punctured Riemann surface, and we'll consider Q correlators of a double algebra. And in fact, these were defined by Edward Frankel and Nikolai Reshetikhin in the original paper. So they look like this. They're correlators of some chiral vertex operators. And the double algebra vertex operator that you insert at a point x is labeled by the same data as on the electric side. So it's labeled by representation of the Langlands dual group. In addition, these magnetic correlators, they have some additional operators inserted, which we'll call Qs. These are labeled by simple roots of the electric algebra, and they don't depend on the insertion points on the Riemann surface. They integrated. They come from. They don't depend on them. Anyway, so we will prove this correspondence for any simply laced Lie algebra, and we'll spell out the steps one needs to do to prove the general case. Furthermore, in the conformal limit, if corresponding to taking Q deformation away, you get back the quantum geometric Langlands correspondence, and then if you go back to the critical level and infinite coupling on the double algebra side, you recover the geometric Langlands. So it contains them both. Okay. Now, it turns out that these Q-conformal blocks of the electric and magnetic chiral algebras are partition functions of little string theory with defects. The conformal limit of little string theory, in which it becomes this theory X, coincides with the conformal limit of the chiral algebras. And okay, so for now we'll specialize for G being of ADE type, so a simply laced Lie algebra. And we'll take little string theory associated with such G on a 6 manifold, which is a product of a Riemann surface and R4. And the Riemann surface will be the same Riemann surface that the conformal blocks live on. The defects are subpointed at points on C, the same points where we put the vertex operators. And in addition, they're supported on one of the two complex planes in R4. So these defects are codimension 4 in the 6-dimensional space. So the partition function of the 6-dimensional little string theory vanishes in the absence of defects. And with the defects added, it equals to the partition function of what turns out to be a quiver gauge theory supported on the defects. So the theory on the defects turns out to be a quiver gauge theory on C times a circle, whose quiver diagram is based on the Dinkin diagram of the Lie algebra. And these theories have 16 supercharges, so 8 supercharges, I apologize. Okay, so now in the quiver diagram of G,
The Dinkin diagram or the intended Dinkin diagram?
it's the Dinkin diagram, the finite of the actual Lie algebra, not the affine one. So for each node, you get a pair of finite dimensional vector spaces. And the ranks of these vector spaces will be determined by the weight of the representation of LG in which the conformal blocks transform in. So the data of which quiver you take depends on which conformal blocks you want to study, just by a representation theoretic aspect of it. Okay. Now, this class of gauge theories was originally considered by Nakajima, who showed that the quantum affine algebra acts on K theory of a variety which he associated to the gauge theory. This Nakajima quiver variety is a hyperkähler quotient, and which he defined, and you can read it off from the quiver. From physics perspective, this quiver variety X is the Higgs branch of the moduli space of supersymmetric vacua of the gauge theories on the defect. Now, the theory, I said that the theory is a quiver gauge theory on C times S1, even though the defects are supported only on a single copy of C. So the defects are 2-dimensional, but I tell you that the quiver gauge theory is 3-dimensional. This is actually due to a string effect. So in string theory, one has to include winding modes of strings winding around the cylinder. And it turns out that this turns the theory on the defect, supported on C, into a 3-dimensional theory on C times S1, where the S1 is the dual of the circle in C. It's basically T-duality of string theory. And furthermore, the parameters that the Q conformal blocks depend on have both a string theory and a gauge theory interpretation. The positions of vertex operators are positions of defects. From the 3-dimensional gauge theory perspective, they're mass parameters. And from Nakajima quiver variety perspective, they're equivariant parameters. So equivariant parameters of the Nakajima quiver variety will encode the positions of vertex operators. The choice of Verma module state are moduli of the little string theory, and they become parameters of the 3D gauge theory, which turn into Kähler moduli of the Nakajima quiver variety. They're just the same. There's no fancy map. Furthermore, the parameters that enter the definition of the algebras, remember, there was H bar in the quantum affine algebra, and there's a Q for the step of, there Q, T, and H bar correspond to the choice of background that a little string theory is placed on. Q and T come from equivariant rotations of the two complex planes in the 6-dimensional space, and H bar depends on them. It's not independent. H bar is like a product of Q and T inverse. Okay. Now, we get some mileage because the partition function of the quiver gauge theory on C times S1 has a precise mathematical formulation in terms of quantum K theory of the Nakajima quiver variety X. So quantum K theory of Nakajima quiver varieties generalizes Gromov-Witten theory, and the flavor of it we need was developed a few years ago by Okunkov with Maulik and Smirnov. It's a variant of the theory that Giventhal studied earlier. But in this case, one crucial use is the fact that X is a holomorphic symplectic variety. And the invariants are Euler characters of certain vector bundles of a moduli space of stable quasi-maps to X. Furthermore, one works equivariantly with respect to the maximal torus of rotations of X that preserve its holomorphic symplectic form, and H bar, which scales it, and furthermore by with respect to rotations of the domain curve. So the domain curve is C, since we studied the theory in C times S1. Okay. Now, depending on the boundary conditions at the T2 boundary of the three-dimensional space, the partition functions of the 3D quiver gauge theory on C times S1 gives you either the electric or the magnetic Q-conformal blocks. In fact, the very most basic object of quantum K theory is what's called the vertex function, which we'll denote like this, which is generating function of equivariant counts of quasi-maps from C to X of all degrees. So it's an analog of Gromov-Witten partition function on a P1 minus a point or a disk. The K-theoretic vertex function of the Nakajima quiver variety turns out to compute the magnetic doubly algebra conformal blocks, and actually manifestly so. And this is something we prove in this paper with Frankel, with Edward and Andre. So the doubly algebra blocks are correlators of some vertex operators, which are given explicitly as integrals over the free fields. And the integrals come from the fact that the Q operators are integrals of some more basic objects, screening charges, screening carbons. Now, the integrals, from the point of view of counting of quasi-maps, come from thinking of maps to X in geometric invariant theory terms. So one studies quasi-maps to the pre-quotient, and then projecting to gauge invariant configurations leads to integration of the maximal torus of G. It's very direct. Now, since it counts quasi-maps from a manifold with a boundary to X, this vertex function is really a vector, and it's valued in equivariant K-theory of X. So we show that there is a choice of contours of integration such that computing integrals that you get from doubly algebra by residues, you get components of the vertex function. So you have, on the left-hand side, you get some choice of contour of integration, basis of choices of contours of integration. And here, you have some choices you put in at infinity of X, of C. Okay. So that's for the magnetic side. On the electric side, a way to characterize electric conformal blocks of the affine Lie algebra is as solutions of Kniznik's homological equations. That's in fact the best way to think about them. And you want solutions of the Kniznik's homological equation that are analytic in a chamber of position space, corresponding to a choice of how you separate the insertion points and take them off to infinity. The deformation of Kniznik's homological equation corresponding to replacing the affine Lie algebra by the quantum affine algebra gives you a difference equation, and this is the quantum Kniznik's homological equation, which was discovered by Igor Frankel and Reshetikhin in the 80s. Now, a key result of quantum K theory, due to Akunkov and building on his earlier work with Maulik, is that the K-theoretic vertex function of X, in fact, solves the quantum Kniznik's homological equation corresponding to the quantum affine algebra. Now, more precisely, a single conformal block of the quantum affine algebra is itself a vector. And you generate it from picking a component of the vertex function and differentiating, or placing extra insertions at at the origin of C. Okay. So in this way, you can generate the entire fundamental solution of the QKZ equation. Okay. So we're almost finished. Now, so the solutions that of the QKZ equation that you get in this way are not themselves conformal blocks, because what you get from just counting maps is not holomorphic in any one chamber of equivariant parameter space of X. It has no reason to be. So it's a solution, but not with no nice analyticity properties. So instead, on general grounds, you expect that there's some linear change of basis depending on the choice of chamber, such that from the vertex functions, you get, we'll call them L vertex functions, which will solve the same. So these are constants or Q constants, but that the L vertex functions, they solve the same difference equation, but they'll be holomorphic in a chamber of choice. Okay. Now, the surprising thing is that not only do we know this change of basis, in fact, we know it because it has a geometric meaning. The linear map that will produce for you conformal blocks of the electric algebra from the magnetic one is computed by what's called elliptic stable envelopes of an Nakajima-Quiva variety, which is recently discovered in my work with Andre. So these electric stable envelopes provide, they're simply a choice of basis, right? But it's a choice of basis in equivariant elliptic cohomology of X. And they generalize the stable basis in cohomology and K-theory due to Mallik and Kunkov. And this explains why it's that a nice choice of basis if you want, right? Okay. So in this way, we get an explicit geometric description of both the Q-conformal blocks of the electric and magnetic algebras and the map between them, corresponding to any simply Lie algebra. Now, you could say Langlands correspondence for simply Lie algebra is a little bit boring because L, G, and G are the same. But from this, you can extend that to non-simple Lie groups when G and LG are not the same Lie algebras. So you use the fact that non-simply laced Lie algebras can be obtained from the simply laced ones by using an outer automorphism from the simply laced Lie algebra, which is called G0, using an outer automorphism. And little string theory tells you exactly what you need to do. So general fact is that this outer automorphism acts by involution of the Dinkin diagram and gives you non-simply laced.
I think the algebraists know this too. The algebraists know they didn't need.
Oh, of course, yes, everybody knows this. The one thing you need to know is how to implement the involution in the geometry.
Well, I think Grothendieck knew that too. This way of understanding.
Sure. But you see here, I have a choice. I have two different choices. I could put a twist. So we'll study a little string theory of type G0, and we'll put a twist. So that ends up permuting the nodes of the Dinkin diagram. But we have essentially two non-trivial choices. You can either put it around the Riemann surface or around C. You want to put it around one of the, and in fact, you have two more choices, because one of these copies of C is where the defects are, and the other one is not. So it turns out you want to put the twist where the defects are, and that is completely uniquely fixed to get Langlands correspondence by string theory. Okay, so this implies that correspondence between Q-conformal blocks of these electric and magnetic algebras should follow by generalizing elliptic stable envelopes to H equivariant setting.
What is H here?
H is this involution. So you just work equivariantly where, in studying your quasi-maps, you rotate the disk. As you, so as you go around the disk, you implement the involution on the...
Order 2.
Yeah, that's right. Except for D4, which is order 3. Okay, now Kapustin and Witten explained that understanding of geometric Langlands correspondence should be tied to understanding of S-duality of a four-dimensional Yang-Mills theory with maximal supersymmetry. S-duality exchanges electric and magnetic fields and inverts the coupling constant, so taking a weakly coupled to a strongly coupled theory. Now, to derive S-duality, one actually needs a little string theory. So Yang-Mills theory arises in a limit of a little string theory compactified on T2 times a 4-dimensional background. For our purpose, the 4-dimensional background will be C, the Riemann surface, times R2. And it was shown by Waffa in the 90s that S-duality of 4-dimensional Yang-Mills follows from T-duality symmetry of little string theory on a torus. You can understand a lot of it from its point particle limit, the theory X, but to actually derive it, you need little string theory. And you understand it clearly if you think about the non-simply laced case. Okay. Now, this is probably in part why one can make progress on Langlands in the context of little string theory and this quantum Q Langlands correspondence. Again, the ingredients we use here were available since the 90s. All representation theorists knew them. Everybody who worked on Langlands knew them. But they were not put together the right way. You needed insights from geometries and gauge theories. Okay. Now, in the remaining time, I want to tell you about applications to knot categorification program. Now, we won't have to go too far because the two-dimensional conformal field theories whose Q deformations we have been studying underlie Reshetikhin-Turaev Witten invariance of knots. So, to get invariance of braids, for example, one wants to start with conformal blocks of LG hat on a Riemann surface, such as C, and we want to actually study, and we want to vary positions of vertex operators over an interval. Okay? And this way, you produce the braid. So this blob is the Riemann surface, and the red direction is the interval direction. As go along the interval, you vary the positions of vertex operators. That's the standard construction. Monodromy of conformal blocks, viewed as solutions of Knižnick's homological equations, leads to quantum group invariance that Reshetikhin and Turaev associate to this same picture. If you want knot invariance as opposed to braid invariance, we want to study matrix elements of braiding matrices between pairs of conformal blocks. So there's a braiding matrix, and then we sandwich it between a pair of conformal blocks that correspond to fusing vertex operators into copies of trivial representation. And this choice of fusing into copies of trivial representations provides the matching of the endpoints. To categorify Reshetikhin-Turaev Witten invariance, one would like to associate to conformal blocks one obtains at a fixed time slice objects in some differential graded category. You want it to be graded so that you can keep track of Q, that the knot polynomials are polynomials in. And to tangles, you want to associate functors between categories. Moreover, we would like to do this in a way that gives you back Reshetikhin-Turaev Witten invariance upon decategorification. Now, physics provides a roadmap to this problem by starting with the 6-dimensional little string theory associated with Q deformation of the affine current algebra, and in fact of the double algebra too, and then taking the Q to 1 limit. As I mentioned before, the Q to 1 limit coincides with the point particle limit of the 6-dimensional little string theory, in which it becomes the 6-dimensional conformal field theory, theory X. Okay, so let's do it and see what happens. Well, it follows that conformal blocks of LG hat and the double algebra are partition functions of this theory X on a 6-manifold, which is a product of the Riemann surface, where you studied the conformal blocks on, times R4, with defects that are supported at points on the Riemann surface as before, and one of the two copies of C. We are not changing that. The same setting, the same conformal block. Just the actual conformal ones as opposed to the Q deformations. Okay. Moreover, as before, due to supersymmetry, we only use supersymmetry there, the 6-dimensional theory X localizes to theories on its defect. Now, theory X is a point particle theory. So a theory on a defect that's supported on, in 2 dimensions is a 2-dimensional theory. The price to pay by taking the limit is the defects themselves are no longer described by gauge theories. And they don't have the simple direct description as was the case in little string. So as a symptom of this, the description of conformal blocks in terms of enumerative geometry of Nakajima variety X breaks down. In fact, the entire enumerative geometry breaks down because X becomes singular. And one way to see that is that the degree counting parameter goes to 1 in the same limit as you take Q to 1. Okay. So to make progress, one has to have a different description of the same physics. Now, in little string theory, the theories on the defects was a 3-dimensional quiver gauge theory. It became 3-dimensional due to these string winding modes, which by T-duality gave it an extra dimension. Now, it turns out that there are 2 natural holomorphic symplectic varieties that you can associate to such a 3D quiver gauge theory. One such variety is the one Nakajima defined, and from physics perspective, this is the Higgs branch of Accio. The other one is so the Higgs branch will denote it by X, as we have been. The other one is the Coulomb branch of Accio, which will denote by X check. The Coulomb branch turns out to be, for this class of theories, is known and part of due to work of Nakajima and Bravelman and Finkelberg. But the Coulomb branches are resolutions of certain finite dimensional subspaces of affine Grassmannian associated to group G, whose Lie algebra is the Lie algebra with the Lie algebra G. And mu and nu here, you can read them off from the definition of the quiver. The 2 holomorphic symplectic varieties X and X check live in different dimensions. And between them, the roles of Kähler and equivariant parameters get exchanged. So I'll call A the Kähler parameters and lambda the Kähler parameter space, moduli space, and lambda the equivariant moduli space. So they get exchanged like this. Now it turns out that conformal blocks of the affine current algebra associated with LG have a geometric description. And they're nothing but generating functions of holomorphic maps from C to X check in equivariant Gromov-Witten theory of the Coulomb branch. So we'll just study Gromov-Witten theory of the Coulomb branch equivariantly. The positions of vertex operators now become Kähler module of X check. And one works equivariantly with respect to scaling with respect to torus. Lambda part of it preserves the holomorphic symplectic form, and again we have a part H part that scales it. And this part that scales it will be crucial to get knot invariants that are this with a sum of sloppy notation. My H bar and Q that people use in defining knot invariants, Reshetik and Turai-Witten knot invariants, I mix them up in this part of the talk. My notation is not completely clear, consistent throughout. Anyhow, so this lambda, which becomes equivariant moduli of X check, was also Kähler moduli of X. All right. Now, so conformal blocks then are just Gromov-Witten counts of maps from C to X check. The dependence on the conditions you place at infinity make them valued in equivariant K-theory of X check. And braiding matrices of LG hat that have now a geometric interpretation. They capture monodromy.
What was T in that slide? KT? Was that the maximal torus?
Yeah, we'll work equivariantly with respect to the maximal torus. This one, sorry, this should have been yeah. So you work in equivariant Gromov-Witten theory.
I got a bit confused because
Yeah.
I thought the conformal blocks were vector spaces. Is it that dimension which is the?
Yeah. So each conformal block itself is a vector space, and to get which conformal block you get is a choice that you put in at infinity of C. Okay. Now to get a vector, you need to in addition place some insertions at the origin. So I'm suppressing those. Those are kind of boring. In particular, they don't play an interesting role for braiding. All the interesting braiding happens in the space of conformal blocks. They're kind of two orthogonal matrices, right? The braiding that actually acts on the conformal blocks geometrically comes from.
When you say the conformal blocks are the counts of maps, what?
So
counting the maps.
So we'll count map C to X check. We have a space of conformal blocks. Okay, which element of the space of this vector space of conformal blocks is this. Okay, there's an additional choice of what you put at the origin. That's going to be determined just by cohomology of X check, equivariant cohomology of X check. But at an infinity, it's equivariant K theory because there's this extra circle. Okay, so really, I'm cheating here a little bit to get a conformal block which itself is a vector, and in WZW, or you'd have to place in additional insertions. But for purposes of understanding braiding, which acts on the space of conformal blocks, I only need to worry about infinity. That's why I'm suppressing what happens at the origin. We can we could carry the whole thing through with insertions at the origin as well.
That would give you matrix elements versus vectors. The elements which determine things are given by two coordinates, I and j, and these pick out particular elements, which are the coefficients, which you'll sometimes work with. But if you take the whole row, you'll get the end product.
Right. I mean, in the end, so the interesting braiding happens in the space of conformal blocks. We want to understand what happens to these solutions of K's equation, right? As you vary the parameters of the insertion points, right? And the fact that equations are vectorial are kind of orthogonal to that question. Okay, so the braiding matrices capture the braiding matrices capture monodromy of Gromov-Witten vertex functions as you vary Kähler moduli of X check. And so there are also monodromy matrices of Knizhnik's homological equations for LG hat, which has a geometric interpretation as the quantum differential equation of X check. And this fact was first shown by, in some special cases, by Viscardi, who was a postdoc at Berkeley. And actually, his observation was crucial for this work. I learned it from him first. Okay, now categorification of braid and notch invariants follows from this geometric description of conformal blocks. See, now that you have geometric description of conformal blocks, you have no more choices about how to categorify, which approach do you take. The boundary condition at infinity of C is an object in the derived category of T equivariant coherent sheaves of X check. And its K theory class is the object of the corresponding complex of coherent sheaves is the choice of conformal block. There's the action of braiding. So for physics, the action of braiding matrices on equivariant K theory of X check lead to autoequivalences of derived categories of equivariant coherent sheaves for any, in fact, smooth holomorphic symplectic variety of X check. That's a conjecture by Bezrukhavnikov and Okunkov, but from physicists' perspective, it has to be true. This geometric description implies that categorified knot invariance arises homes between complexes of coherent sheaves on X check, the complexes of coherent sheaves associated with these perfect matchings. Now, so the key thing here was to understand the geometric interpretation of conformal blocks themselves in terms of Gromov-Witten theory. Once one understood that, the path was clear. So let me explain. How one shows that. And I'll do this because it's interesting for actually two reasons. So bear with me, even though it's late in the talk. The first reason that's interesting is that the proof involves an instance of what physicists call three-dimensional mirror symmetry. Mathematicians refer to it often as symplectic duality. So it's a duality believed to relate computations on X and X check. Okay, so so we'll go back to little string theory world and recall that there, the elliptic stable envelope. So it turns out that the elliptic stable envelope map, we saw this in fact in the first part of the talk. The elliptic stable envelope map of X exchanges the roles of scalar and equivariant moduli of X. It maps a basis of vertex functions that is analytic in scalar parameter to a basis that's analytic of X to a basis that's analytic in equivariant moduli. Now, the object defined in this way gives, as we saw before, gives a usual basis of Q-conformal blocks of UH bar of L hat. This should not be X. Of the quantum affine algebra. Okay. And it gives a basis that's analytic in it gives a basis that's analytic in equivariant moduli of X, hence in scalar moduli of X check. Okay. So a theorem which Andre and I can prove whenever X check itself is an Nakajima variety is that the L vertex defined in this way by the elliptic stable envelope map from the K-theoretic vertex function of X is in fact the K-theoretic vertex function of X check. Okay. So the stable envelope map maps the vertex function of X to a vertex function of X check. So this statement is an instance of three-dimensional mirror symmetry, which relates these 3D computations on X and X check, or in this case, 3D for physicists is K-theoretic. Okay. So it follows from that in the conformal Q is equal to 1 limit, the Q to 1 limit, the K-theoretic vertex function of X check becomes the equivariant cohomological vertex function of Gromov-Witten theory of X check. So we understand this in K-theory limit first, and then take Q to 1 limit. Again, this is not the most the strongest way of proving this, but it's an instructive one. So it becomes the equivariant cohomological vertex function of Gromov-Witten theory on X check because the QKZ equation itself becomes the KZ equation, and hence you get the identification with conformal blocks. Okay. The limit is simply designed to do that. Okay. Now, the second reason is interesting is that you actually get a second description of categorification of knot invariance. In fact, you'll recall that Q-conformal blocks of the quantum affine algebra and the doubly algebra, they solve the same difference equation, and hence, up to conjugation, they have the same braiding matrices. And they have geometric interpretations in terms of Well, for the doubly algebra blocks, they were just vanilla k-theoretic vertex functions of x. For the quantum affine algebra, they were k-theoretic vertex functions of x check, and they were related by three-dimensional mirror symmetry. In the q to 1 limit, they become conformal blocks of LG hat and the doubly algebra, which solve the same differential equation, the same KZ equation. Hence, they have the same braiding, they have the same monodromies, and they lead to the same quantum knot invariance associated with LG. So you get a second way of getting knot invariance just from conformal field theory. Now, the fact that that conformal blocks of LG hat and doubly algebra give the same braiding matrices and same knot invariance was known for a while when G was A1. But the general AD case was proven as part of the quantum Langlands correspondence. And the general case was conjecture. It's part of the Q Langlands conjecture. Okay, now, so we've seen that conformal blocks of LG hat have a geometric description in terms of Gromov-Witten theory of X check. Do these have a geometric description? It turns out that they do. And the two descriptions are related by two-dimensional mirror symmetry, the vanilla mirror symmetry that mathematicians know. Again, remember, they solve the same differential equations. The geometric interpretation of conformal blocks of LG hat is in, I just already said it. Again, to just say it one more time. So of LG hat is in terms of Gromov-Witten theory of X check. The geometric interpretation of conformal blocks of the doubly algebra is in terms of Landau-Gisberg model of B-type. The Landau-Gisberg model is known in complete generality from integral representation of conformal blocks of doubly algebra, or equivalently from the q to 1 limit of the k-theoretic vertex function of x. So something interesting happened. X, the description in terms of x is not useful anymore because k-theory to x is not good because x is singular. But it turns out that the integral representation of this vertex function in fact describes the Landau-Gisberg model of B-type. The conformal blocks themselves are partition function of Landau-Gisberg theory on an infinite disk with A-type or thimble boundary conditions at infinity and a B-twist in the interior. So a theorem whenever X check is in a Kojima variety, and a conjecture in a general case, which again I'm sure it's right, is that the doubly algebra Landau-Gisberg model is a 2D mirror of the slices in F and Grassmannian. Okay, so then knot invariance obtained from LG hat and doubly algebra conformal blocks are equal, and they're in fact related by two-dimensional mirror symmetry of the underlying theories. The Landau-Gisberg model in its category of A-branes gives a mirror approach to categorification of knots, mirror to the one based on derived categories of or B-type branes and slices in F and Grassmannians. Okay, so little string theory and the fact that you can really understand the theory, in particular the fact that its defects have a description in terms of gauge theories, leads to unification of many previous approaches to knot categorification. So the approach based on derived categories of slices in F and Grassmannian was first put forward by Chemnitzer and Kautis in type A, and then many people followed up. The two-dimensional mirror Landau-Gisberg approach is presumably related by Calabi-Yau Landau-Gisberg correspondence to Fukaya categories approach of Abu Zaid, Smith, and Seidel. When G is A1, the Landau-Gisberg approach to categorification was also conjectured by Witten and Gaiotto. And the entire story, in fact, is related to a more involved approach by Witten based on five-dimensional gauge theories. These five-dimensional gauge theories that Witten studies, are, as physicists well know, arise as circle reduction of theory X. And Witten describes the problem from perspective of the bulk theory, and we describe it from perspective of the defects. And this defect description is easier by
Is this five-dimensional theory reading the work of Sergei Gukov?
Yes, that's right. So Witten's work is following up on earlier work by Gukov and Waffa and Albert Schwartz, certainly. And in fact, that is a follow-up on an earlier work by Oguri and Waffa. But to be completely fair, Gukov, Waffa, and Schwartz, they emphasized their approach. Their story is really interesting for home fleet. They focused on large N dualities and sort of the dual description. Witten rightfully said that no, we should actually be able to do E-type as well, and just study sort of the original side. But which physics setting we should study, it's really we learned from Oguri and Waffa going way back. In fact, coinciding with Kovanov's development of not homologous. Okay, so this is, yeah, so hopefully I've convinced you that the gauge theories, and indeed these gauge theories really have the same supersymmetry as the ones in Simon's work, just on 1 or 2 dimensions lower. So, okay, thank you so much.
I believe one question in this area is whether one could define the categorified invariance for knots in general 3 manifolds. Is that something which?
That's a great question. So, with this, you could go up to I'm sad to say tori. Maybe tori and S1 cross S2. But a completely general story would be hard this way, because the theories on defects are no longer gauge theories. So I don't think it's going to be easy. If you take it to torus, it becomes gauge theories 1 dimension up, so that's really easy. But, yeah.
If I can, again, 40 years ago, I suggested to Witten this program should be developed. It took 40 years to develop. I'm glad to see it developed so well. That's one question. Secondly, I admire great skill, all this algebra that's been inducted. I'm not an algebraist. I'm a geometer. And lastly, the really interesting problem here is, of course, not the geometric Langlands, but the real Langlands, real number theory. And so the real problem is how to do this thing over the integers. And of course, we know from the work on the goal, solve the real Langlands story using like Hitchin's work, it comes from here, that there should be such a thing. So the stage is all set. All this machinery should make sense, should work over spec Z. And then you will get into real number theory, real Langlands, and all this will be part of a program that stretches. And I conjectured that at the same time as I conjectured the other idea. So I think number theory is still waiting for the applications. So geometric Langlands is just toe in the water.
Yeah. Right, and in fact, right, first witness paper on Langlands was in a conformal field theory setting, right? Following. So yes, we will listen.
I offer this as a challenge to the young students here.
Okay, by tomorrow morning, please. Okay, great. Let's thank Mina again.